Hello everyone, Richard Walding here. I'm just going to run you through a presentation I did at the University of Queensland and at Griffith University. It's aimed at helping students to realise ways of not losing marks. Not so much about how to gain marks on the external exam. This is the Queensland external exam I'm talking about in physics, but rather more about how not to lose marks. There's little things that cause students to lose marks, and I'd just like to point out some of these sorts of things. So let's have a look. This is the presentation I did. Now, I'm a marker for the senior physics external exam. I've been doing it for 4 years now. These are just some tips I've picked up over the time. Also, when I teach my own classes, just little things I realise that they're doing wrong and they're going to lose marks. But it's also from the subject reports that the QCAA, the Queensland Authority for looking after the exams, puts out every year. So just a few things like that. So let's have a look. Now, I did this presentation also at the Tertiary Studies Expo for students really in grade 12 who are contemplating which course to take for after grade 12. So their parents and students turned up for that. This was in July in Brisbane, and so I've used some of that as well. So let's have a look. One of the key things, now this is drilled into students all the time, but one of the key things you've got to watch out for is cognitive verbs. Now, there's a number of cognitive verbs and they're all sort of listed in, basically you can get them in the syllabus or in the documents provided by the authority. A couple of the main ones for physics are the explain, describe and define. Now, define has been used in the last couple of years, but with the new syllabus coming out next year or later this year, define won't be one of the cognitive verbs. The students aren't expected to define any of the glossary items. So it's mainly explain versus describe I want to talk about. Now here's an example of a good question that does that. Now this is out of the 2021 physics paper. And it said, explain how transformers work. So that's the cognitive verb is explain how transformers work, and the question has given students an idea that it has to be in terms of Faraday's law and induction. Okay, so you've got to explain and you've got those two terms. So explain is a little bit different to describe. So a lot of students here lost marks because they were describing rather than explaining. So let's have a look. It was 3 out of 3 for this, 3 marks for this question. And you had basically 3 things to do, or four things to do to get those marks. Okay, so here we go. I've said here, you've just got to provide an explanation, not just describe. So, and again, that's where the students were getting 2 out of 3. So that's just 1 mark for, it's not that they didn't know it, it's just they weren't sure that they had to write it. But if they know what explain means, it gives them a good clue. So when you have to explain something, there's 3 parts to it. You have to identify what you're talking about. So identify the term or the scenario, whatever the question's about. Then describe it. That's the first part. So you're describing, and that's a lower level cognitive verb, if you like. And then you're going to elaborate. So after you've described it, you're going to elaborate. Now, elaborate means to talk about something else related to the explanation, to the description that helps fill out you're showing your understanding of what's going on. So that's often written as IDE, and the D and the E part, the describe and elaborate, make up the written response. So that's what the students will have to do. Okay, so for instance, when you were asked to explain the transformer, the first thing is to describe what's happening in the primary. Now you realise there's a primary and a secondary, and the two things that tie them together are the number of turns and Faraday's law. So what you'd be saying is that in the primary there's an alternating magnetic field or flux. So you've got to mention that it's changing. Now you realise, of course, transformers need a changing flux, changing magnetic flux. They won't work with the if it's a constant flux. So you've got to have some sort of change. So that's the first thing to do. So you could say it's an alternating current, but you really need to talk about the changing and alternating magnetic flux or field. So there's your first mark. Now the second mark is what's happening in the secondary. So you'd need to say that the changing magnetic flux in the primary induces a changing magnetic flux in the secondary, which induces a current, or produces a changing magnetic flux in the secondary, which induces the current. You need to use the words induced. So you're trying to link the two together by the changing flux, and one's inducing the change is inducing a current in the other one. So there's the two marks. Now to get the third mark, you're given the clue that it has to be something about Faraday's law. So Faraday's law is about the rate of change of flux. So you'd have to say something like the EMF in the secondary is proportional to the rate of change of flux, or as the rate of flux, as the rate increases, the EMF increases. You've got to show that they're linked by some sort of proportional relationship. It's no good just saying they're related. Okay, you want to say that they're proportional, because that's exactly what Faraday's law talks about. So don't say related. You've got to be more specific than that. So there's basically, you need that elaboration plus a second one, and you need to talk about the number of turns. So you could talk about the ratio of the number of turns in the primary and secondary, how it could be a step up or step down transformer. A simple statement would be greater the number of coils in the primary leads to a decrease in voltage in the secondary, or something like that. It all depends on the ratio of the loops or the turns in the primary and secondary. Okay, and I've said here voltage is okay for EMF because it's understood what it's meant. So that's an example of how you do it with explain rather than just describe. Now, here's another one. This is it's actually question 21. It's 2 marks this time. This is from the 2022 paper, and you can almost, as you read the first few words, you know it's coming. It's hot iron bar, has a deep red colour, and when it's hot, and as it's heated further, it changes to orange. Explain. So you ask this time to explain the colour change, and you're told what you have to do it in terms of blackbody's radiation, or Wien's law, or something related to that. So you've identified it. It's a part of quantum theory. Now, it's not electromagnetic radiation from the magnetism topic, okay, even though it's talking about the colours. We're not talking about electromagnetic radiation, the spectrum of light or anything like that. It's mainly about the blackbody radiation part. So the description might be that the iron bar is a model for the blackbody radiation, and so as you heat it up, the object's thermal energy is converted into radiation, and the spectrum is due to the conversion of that thermal energy. More thermal energy, the greater the spectrum shifts towards the blue end of the spectrum. Okay, so that's basically, you're just sort of describing the setup, and then you're elaborating. And here we are. This is Wien's law. As the temperature increases, the peak wavelength gets shorter, and that means the colour changes from the red to the blue end, so going towards the blue end, so red to orange in this case here. And we've stated Wien's law. The wavelength lambda is equal to Wien's constant divided by the temperature in Kelvin. Okay, so you can see what you'd need to get the 2 marks there. Okay, now students would get 1 mark typically for that and then struggle to get the 2nd mark. So that's an interesting way, a good question to look at for that. Okay, now another one that students have had a lot of problems with is justify, and you actually lose a couple of marks here. Justify is more than just particularly in this case I'm talking about a hand rule, so Fleming's left or right hand rule and or the right hand slap rule or palm rule, whatever you'd like to call it. So those sorts of rules are ways of working out the direction of currents or fields or whatever, but they're not justifying it. You want to look at the theory that went behind the hand rule and talk about that rather than the hand rule. So for instance, here's a question. Now this diagram, I've just taken it out of my textbook, the Oxford textbook, just so you don't think I'm using copyright materials. But on the QCAA exams, you'll always get questions about changing flux and induced currents. So here all it is just a loop of wire, basically a U-shaped loop of wire and a bar across the middle, and that bar is pulled sideways. Okay, now I've given some dimensions here, and we've got the magnetic flux, the magnetic field strength is 0.2 Tesla into the page. That's shown by the tail feathers, if you like, the crosses indicating it's into the page. Okay, so the question said, what happens when you move or a typical question would say, what happens when you move that rod along? So you're increasing the area, and you have to work out which way the current's going. Okay, now I won't go through how you do it, but that's the sort of question you'd have. Draw a conclusion about the movement of charge in the rod. So you'd either say up or down or not no movement at all. You'd use a hand rule possibly, or Lenz's law, you'd work it out from that. But you can't just say the current, for instance, or the charge moves from B to A and then justify it by saying I use Lenz's law, or I use the right-hand slap rule, or the Fleming's right-hand rule. That's not justification. That's just basically how you'd go about working it out. So you need to talk in terms of opposing the change in flux. So the setup, there is a change in flux through the loop. As the loop gets bigger, there's more flux lines through it. So flux is increasing. So you'd have to talk about how the system would oppose that change in flux by producing an opposing field. Okay, so that's a long way to get at the point. Don't use the hand rule or even the formula. Don't say, well, this formula is how I justify the direction of the current or something like that. You need words that describe it properly. Okay, now another trap students get into is changes to definitions. Now what they'll do is give you a question where they'll try and trap you, or not so much trap you, but they'll try and get you to show you understand what's going on. So here's a question here. It says leptons do not experience, and they give you a number of different forces, and leptons do not experience, hang on, that's not right. The answer for this is, that star shouldn't be there, it's on B. The answer is the strong force. So leptons, such as electrons, muons, tauons, or electron antineutrinos and so on, don't experience the strong force. And you see about half the students got that right. Now these figures come from the report, QCAA subject report. So about half the students got that right. But you think, well, that's a pretty straightforward definition, but where they've trapped a few students is by using this word strong force. Now the syllabus glossary and or the syllabus itself calls it the strong nuclear force. And that's what I did in the Oxford textbook. I followed the syllabus and called it the strong nuclear force. Some people abbreviate it to the strong force, but in this question they've abbreviated it to strong force, but probably trapped a few students by who thought of it's possibly other forces. Okay, so they are affected by the gravitational force because they have mass. Not all of them are affected by the electromagnetic force, but any of the charged leptons are, so that's a reasonable sort of answer. So one of the comments made by the QCAA in the subject report, they gave some advice. Expose students to multiple choice questions with options that contain variations on the exact wording of the definition in the glossary. So that's what's happened there, and so just be prepared for that, and don't expect the definitions to be word for word with the glossary. And in the new syllabus that's coming up, there won't be a glossary for physics terms, so this sort of question you won't see quite as much, I don't think. Okay, let's move on. Another one is the unit trap. The units in the sort of meters and seconds and so on. Here's a good example. Now this is just in the orbital section, in the orbits, satellites travelling at a certain speed, a certain radius in its orbit, and the question is what's the orbital period. Okay, so the answer is that one, and 41% of students got that right. But have a look at this. 44% got it wrong. Okay, so something happened to trap them. Now what trapped them was that when you work it out in seconds, it comes to 1.64 by 10 to the 6 seconds. Now I suspect students saw that on the calculator, noticed that number as one of the options and just said, yep, that's it. But the number's right, but that's in seconds. So if you convert to hours, it comes to this one here. And so 41% of students did it. 44% just left it in seconds and assumed this was it. So that's a trap. So you've got to watch out for those things. Here's another one. This is off the alternative sequence exam, the 2021. Now, the trap here, this looks like the current versus voltage. It looks like an Ohm's law sort of question. But if you notice there, whoops, that's in milliamps, okay, not in amps. So when you're working out the current, or when you're working out, say, the resistance or something like that, just be aware that's in milliamps. Okay, so that was a trap. This is particularly important for students whose calculators go flat, or the batteries go flat before the exam, or they lose it, or they can't find it, or something like that. I'm saying here you need to know your calculator, because some of the questions, the sort of calculations you do can get tangled up. So this question, it's not so important that you understand what the question's about, it's just that the formula looks like that. Okay, so it's just the force between two charges. But what you'll notice is some of these numbers at the bottom here, look, this is the distance apart squared. So when you're trying to enter this in your calculator, often you end up squaring just the last part and not the whole thing. So you've got to watch your brackets. You've got to really understand what you're doing. And students do get they do get confused with this one. That's a big one that students lose marks with, not being able to use their calculator properly. And that often comes because they've borrowed a calculator at the last minute and they're not familiar with it, or they use one provided by the school because their batteries are flat. Okay, you wouldn't be familiar with it. Now, knowing which formula is which is another important one. students often pick the wrong formula. They think they're getting the right formula, but it's the wrong formula. Now, what I do is I print out the formulas, cut them up, and get the students to match the formula with the description of it. I'll make up a description of each formula, or they have to group them together under the right headings and so on. One of the multi-choice questions is often identify the formula which does something, right? You have to pick from a list which formula represents so-and-so. Okay, now often it'll be you're asked to pick the formula that shows a relationship between some concepts, and the other one will be correct, but the others will have the relevant symbols, mass and energy, but will be a different concept. So, for instance, in the short answer paper, students often choose a formula that has all the right symbols, but it's unrelated to the concept in question. Here's an example, for instance. Okay, now which one is it? You'll notice it's something to do with mass and energy. So you'll be looking for a formula with M and E in it. You've got the first one, the second one's got an M and an E. They've all got M and E. But you have to know which one is basically Einstein's mass energy equivalence. That's a statement. That's the name of the formula, if you like. And of course it's the first one, and 86% of students got that right. And 10%, the next major one was 10%. They've found E and M, and they know it's something to do with the speeds, so they've chosen that. And that's out of the glossary. That's the exact term, and that's the formula that goes with it. You might notice that it doesn't have the delta sign in front of the E and the M. And as we saw back on an earlier slide, you can have variations on the exact formula from the glossary, and just be prepared for that. While I'm at it, I should mention that students often use the Rydberg equation to work out something about energy transitions and the spectrum, or the colour of the light, wavelength of light produced during a transition from a particular level to another. Now the Rydberg equation is for hydrogen only, and in the syllabus the formula is there, and in the formula book you'll see the Rydberg equation. But for other atoms, if they've given you a diagram with maybe electron volts for the different levels, you use that. You don't try and apply Rydberg equation if it's specifically, the question doesn't specify that it's hydrogen, so you're using the wrong equation. And the other thing, students do lose marks for getting their mu's and nanos, so the micros 10 to the -6 and nano 10 to the -9. That's in the formula book, but students do get it mixed up. So often you'll lose a mark just by not being able to find the right value or writing the right value down. So that's that one. Another one students tend to get muddled up in is getting their topics mixed up. So look, here's an example. Collection of mesons. This is, if you think about it, this is about evidence for special relativity. But you could easily look at that and you think, this is about moving a distance, some speed of light, and another distance here. This looks like a linear motion question, or maybe projectiles or circular motion. So you'd have to straight away look at that and think, yes, that's special relativity. Now, I've said here, what you can do in perusal time, if you've finished everything else, you're not writing, of course, but you can look through each question and in your head think, that's quantum theory, that's projectile motion, that's centripetal force, and so on. Identify the topic when you've got time just to go through it. Now here's one. A lot of students, they look at a question, they think, I've got no idea how to do that. So they get an NA, which is a no answer basically, or zero. It gives you a 0 mark, but they just leave it blank. And you think there must be some marks you could get. Now, a question like this is 5 marks. Now, often the first couple of marks aren't really that complicated. They're identifying something. It could be identifying the scenario is about hydrogen spectrum or quantum theory or something. What I find is that if you say to students, look, just get started, do something, and what often happens is you all of a sudden start thinking, oh, I remember this, and in your mind you start thinking of links to other things, and once you get started you find it all of a sudden brings other things into your brain. So for instance, you look at that wavelength, you think, what can I do with that? It's in nanometers. Well, let's say what it is in meters. And it could be something as simple as that gives you a mark. Now, I'm not saying it will, but depending on the marking scheme. Or you could look at this thing here in EV, electron volts. You'd say, well, let's convert it to joules. Okay, that could be a mark. Or you could have the change between two levels. And you could say, I'm going to work out the delta E, just subtract the two values. That could be a mark. Now, you probably wouldn't get a mark for each one of those, but you'd get probably a mark for doing one of those in this question. Now, I can't remember the marking scheme for that. So that's a good suggestion. Now, another one is if you can write down a formula when you look at the question, that can often give you a mark. The marking scheme might say identifies a scenario is related to linear projectile motion or something, and you'll have a formula for projectile motion. Or it could be a photoelectric effect. So here's what the marking scheme. This is the marking guide for the external exam. It might say the scenario relates to quantum theory or photoelectric effect. Okay. Now I've said there you write the right formula down, but what happens if and some students say to me, well, I'm going to write every formula down I can. I'm bound to hit one that's right, and I'll get a mark for that. So let's have a look. We'll say it was a question about the photoelectric effect, and the marking scheme said recognise the scenario relates to the photoelectric effect and threshold frequency. Now, that could be because you've written down a formula and you'll get that mark. So if you write down this formula, that's the photoelectric effect and threshold frequency. So you'll probably get your mark for that. I'm not saying you will for sure. It depends on what happens each year. You could, if you wrote that one down as well, that doesn't do any harm because that's a part of the theory behind photoelectric effect. It enables you to calculate the energy if you know the frequency of the photons of the light. I mean, you could even use that one. So if you wrote all of those down, none of those contradict the first one. They're all the scenario related to photoelectric effect. But let's say you wrote that down. Now, it's to do with quantum theory, and it's the momentum of a photon, or you're using it for calculating the momentum of a particle. It's not strictly related to the photoelectric effect. So you're starting to get onto a bit of dodgy ground here. A marker might look at that and think, yep, they know the formulas, but wait a minute, what's this? And if you stray too far, you're never quite sure that the student knows that the scenario relates to the photoelectric effect, or they're just getting confused and putting anything down. Now, say for instance you put that down. Well, that's Faraday's law. Now, that's nothing to do with it. So it's not clear here that you recognise the scenario as the photoelectric effect, because you're putting this one. So you're confusing the marker. You're saying to the marker, well, it's either one of these two, and the marker might have to say, well, you can't hedge your bets. You can't just write down any other formulas and hope for the best. So I'd say get rid of that one, probably get rid of that. You got those three, you probably get the mark, if that's what the marking scheme said. So don't fall for the trap that people often say, just write down as many formulas as you can. It's not going to work. Now the PE effect is, there's always a question on the PE effect somewhere, and it could be a graph or it could be just a definition or something like that, or a calculation. Students often get energy and intensity mixed up. I'll talk about the light having sufficient intensity to emit an electron. It needs the energy. Intensity is just basically the number of photons that are striking the plate. It's the energy that is the thing that causes the change in kinetic energy. So they're different things. The PE effect is not about the law of reflection, even though light is reflected. If you shine light on a metal plate, it can be reflected or it can be absorbed, but students often say, the angle of incidence equals the angle of reflection, and they think that's the main point about the PE effect. Now that won't get you a mark. The PE effect is not about black body radiation, so even though the metal might get a bit hot, it's not emitting radiation as a black body. So you often students think that that's a key point. It's not about electron transitions like in a hydrogen atom and falling from one level to another and giving off a spectrum of light. That's not the PE effect. Photoelectrons are different to photons. Photoelectrons are electrons. They're electrons that are produced by being struck by photons or light. A photon is not a positron. You often see students writing positron, protons and leptons. That's another one that students do, not so much in the external exam particularly. I'm not trying to say what I see. Just in general, when you're talking to students, they get that tangled up. I've had students talk to me about the work function being about the weak nuclear force. I think it's something to do with electrons. Now, you might get a question that's about photons having energy, but if you're trying to describe the PE effect, you need to do more than just say they've got energy. You need to talk about them having energy proportional to frequency. Be more specific. The same students often talk about having light having or the photons needing to have the right amount of energy to dislodge an electron. It's not really the right amount of energy. You need to be talking about them having the right frequency or the amount of energy related to the work function. Okay, and another big one when I talk to students is when they talk about the gold foil experiment and you say, which one? And they don't realise that there's two that are commonly mixed up. There's Rutherford's gold foil experiment where his workers shot alpha particles at gold foil, and that was to identify the dense nucleus. But you've also got the gold foil electroscope. You put a piece of zinc on the top, shine some UV light on it, and you'll get the gold leaves of the electroscope will start to diverge or open up. So it's two completely different ideas. This one, the gold foil electroscope, is the one related to used in demonstrating the photoelectric effect. Okay, so it's no good just saying the gold foil experiment is evidence. You'd need to explain what it's all about. Okay, just a few more. Watch for red herrings. Students don't seem to know what red herrings are anymore, but red herrings are just irrelevant information that's in the question, and it's not so much there to trap you, it's there for you to show that you understand what's going on. So in this question from 2021, there were two diagrams. That's the first one, and what they did was they put a current through these two wires, and this little wire here shot out like that. Okay, and the angle here was 40 degrees. Now, what students do with things like that is they'll think of the formula, which is the force on a wire is BIL sine theta, and they'll say, oh, that must be sine 40, without really thinking it's the 40 is the angle with respect to the field, not with respect to the vertical or anything like that. So that's a tricky one. And if you looked at the marking scheme for that, even just putting the forces down as the vectors in the right diagram, they were being awarded 1 mark for that. Okay, and common mistakes for that is where the wire that moved in the field is being treated as if the movement of that wire is inducing a current rather than the current producing a force on the wire in the field. So getting it back to front. Now, just a couple more here. That's I said was using the formula before, so they use the 40 degrees there, basically putting it into that formula and getting the wrong answer. Okay, we'll move on. Another one is familiarity. Now, when I first read this question on the 2020 paper, I saw the start, twin astronauts and special relativity and so on. I just thought, oh, it's going to be a question about the twins and the paradox about how they age. But when you start reading it, it's not about that, because the twins don't come back to Earth. Okay, so the twin paradox is about arriving back at Earth. This question just uses twins, but one lands on a different planet. So you get trapped by the familiarity. I just, when I was thinking of the answer for that, I just automatically thought of explaining the twin paradox, but that'd be completely, well, not so much completely wrong, but it's not what this question's about. Now, the theory or the idea from teachers is that you're under pressure and you want to save time. So you see twin astronauts and you think, oh, I won't read the rest. I'll save time. I'll just use a shortcut and write about twin paradox. So my suggestion is don't rush into a solution without reading it properly, because that's where you lose the marks. Now, avoid the units in the graphing. In graphing, like I said, you're bound to get a photoelectric effect graph. Well, not every year, but they appear every second year, or I think the past 3 papers, 20, 21, 22 maybe, had graphs. Here's a typical one. Okay, and everyone's familiar with how you do that. You draw a line of best fit. The slope is equal to the Planck's constant, and F0 is where it crosses the intercept here at 0 energy. Okay, so nothing too tricky in that, but just make sure this is in, if that's in joules, right, it might be in electron volts. Make sure this is in, they're in hertz if it's a frequency. So I've circled that. You've got frequency at the bottom and joules up the side, so that's a nice, fairly conventional one. But don't forget where the intercept, this comes through down here somewhere. If you extend it, that value down there is the work function. It's the magnitude of the work function. So let's say it hit there at 4, the work function would be positive 4, not negative. Okay, so it's the magnitude of it, not the plus or minus, or not the minus value. Oh, what did I say there? Oh yeah, some students often think the photoelectrons travel at the speed of light, and that really confuses them trying to use any of the formulas. Here's another one from 2021. Now what they did was put work function along the bottom. So students would have seen this photoelectric effect. They think, oh yeah, kinetic energy. This is just draw a line through there. It's probably the Planck's constant or something. But that's the trap. They put work function there. You can still draw a line through it and get a gradient and work out things. But my comment is don't jump in and think it's one like you've seen in class. Linear graph, you can model it as a linear graph and work out various values that you need. Okay. Another one for the gradient trap. Here's one from 2022. You had to draw a line of best fit. Now that looks pretty much like it. You've got a couple below the line, and this one is almost on the line, but it's about the best I could do. Some below and some above. Okay, and it goes through 0. Now, it doesn't have to go through 0. Some of these lines look like they'll go through 0, and the key thing is don't force them to go through the origin. It's okay if they do go through the origin, but don't force them. The example used in the report showed it, one similar to this. I think it might have been this one. That they made it so it didn't go. Well, they used a student example that didn't actually go through the origin. Now, when you're working out the gradient, use 2 points on the line a wide distance apart. So don't use these two. Remember, you have to use points on the line, not points on the points that are on the graph paper. So you'd have to find 2 points on the line. You just mark them on the line, but don't use too close together. Use one at each end if you can. Now my suggestion is don't use 0, because the examiner or the marker will want to know that you used change in y over change in x. If you just choose a point up here and you think, well, the other point is 0, so I don't even have to write down minus 0 and minus 0 for the horizontal, the marker could think you've just chosen a point and you've calculated the gradient from that point and not used 2 points widely spaced. So just be a bit careful with that. I'd use one at almost at each end of the line. Like so, those 2 points there would be good ones, the ones in red. Here's one. Oh, I've just said that about don't use the 0 if you can help it. Here's the one from the subject report, and the student has chosen 3 points, 1, 2, 3 on the line, but you'd want to use the ones as far apart as you possibly can. If you're using this one here, don't use this one, but use this one down here or further down. I don't know why they didn't use one way down here somewhere. Now here's another tricky one about the axes. This is from 2022. You'll notice it's a PE graph, photoelectric effect, but the x-axis is 1 on lambda. Now this through students because it's not what they expect. You expect a frequency, so even though you're trying to apply your formula, the EK equals HF minus W, it got students into a lot of trouble here. Normally you could calculate the work function based on the intercept, but that caused a lot of mistakes. So the work function would be down here where it cuts, but the trouble is it doesn't start at 0. Okay, so you can't really look at the intercept and extend this line and say, oh, it's cutting here at -0.1, because that starts at 1.6. So you've got to find out another way to do it. You could do it by seeing where it cuts here, and that'd be F0. But here it's labelled as 1 on lambda, so you'd have to convert to work out F0. A bit tricky. I saw 4 different ways of doing it. There's a lot of approaches you can do there. Okay. That was extrapolating, and you can get the F0 value here. Okay. And then I've just shown you how you'd go about doing the question to get the right answer. I won't go through that now. Okay, what's your handwriting and setting out? This is a bit tricky. Some handwriting's really hard to read. Now I've made one up. This is not a copy of anything in the student's work. I've just made one up just to show you the problems you can face as a writer, as a marker. So I made it clear this is not a screenshot of actual student work. That's my handwriting, just to show the point. But you can see this, in this case, this hypothetical student is working out stuff down here, and they get an answer and they realise they've got to go back up here to use the formula, and then crossing stuff out. If I was trying to mark that, you'd see, well, here's the answer. If the answer's right, at least you can then go back and make sure they didn't get it right by accident, and there's enough information in there to support getting that answer. But boy, that's a hard one to decipher. Things crossed out all over the place. So that's the sort of thing that it just takes a bit of extra time for the markers to sort through. But we always, go looking for it. There's not a problem. It just takes time. I've just said when it turns into a big mess, you might like to label the key steps, number the key steps so a marker can follow it through. Okay. Oh, that one was about the work function for the metal. Oh, this is going back to that earlier slide about the 1 on lambda. This is another one. This is the third part of the question, and if you get the first part wrong, you can still pick up your marks. This is follow-through error, the FTE. So don't give up. Even if you see the third one and think, oh, I couldn't calculate an earlier value I need, I've seen people just say, let's call it X, let's call the value I need X. I don't know what it is, but I'm going to call it X and show the working. So you can still get full marks, even if you get part A or B wrong. So just don't give up. And lastly, just be careful with conflicting information. If you saw this question from last year, these 2 graphs, depending on how you do it, you can get different answers. The thing is, if you thought of 2 ways of doing it and you've got different answers, you don't need to do both answers. Just do one. You'll get your full marks if you do it correctly, even if there is another way with another answer. So I'd say ignore conflicting information. Just do the one and leave it at that. You won't have time to do any more. Okay, so that's just a brief overview of some of the things you might see on, ways of saving your marks. I'm not getting too tangled up. Okay, so there were 2 methods for that. One called the asymptote method, and the other one using equal field strengths. And they gave slightly different answers. So that's the end of that. Okay, that's it. I'll leave it there. So goodbye.